Hi everyone, I am Ruben Dallakyan from Armenia, Alikhanyan National Laboratory. First, I want to thank the organizers of the conference for letting me show my talk by video, as I wasn't able to come to Canada. Wish you all have a nice discussion and all the success. The topic I am going to talk is about the geometry of the target holders, which led to high efficiency cooling, locally inclined target holders with high efficiency cooling for Nirta solid target module. A variety of solid targets and modules are used for medical isotope production on cyclotrons. For high-intensity irradiations, inclined targets are used, which have a greater surface for cooling. Achieving as much as possible high activities is one of the main goals of radioisotopes production. For this purpose, high-intensity irradiation is needed, which holds strong requirements for the target cooling system. We use Nirta solid compact target module for irradiation under IBA-C18 cyclotron beam. The general view of the module is brought on the right side. The standard target base or holder for Nirta is a titanium disc with a diameter of 24 millimeters and a thickness of about 2 millimeters. On one side, the disc has a cylindrical recess, target area, in the center with a diameter of 12 millimeters and a depth of about 1 millimeter, as shown on the left. In the standard target module, the proton beam falls on the front side of the target, which is cooled by a stream of helium gas, and the back side of the target is cooled by water under a pressure of 5 bars. How can we improve the Nirta solid compact system to provide better cooling efficiency and therefore higher activity production? And the answer is the following: increasing the cooling surface. The target area part is in form of ribs in both sides. The cooling surface is increased on both the helium side and the water side. We call this a locally inclined target, or LIT. On the left side, the dual axle LIT holder is shown. The word dual is used because the ribs are on both sides. This version is equivalent to a cone by its area. The left one is called dual line, and it is equivalent to an ellipse. Let's watch now to a small illustration with the paper model of the dual line target holder. Here you can see the model of the lead holder and an ellipse behind it. They have equal areas. And this one is another model which can become an ellipse by stretching. On this slide, you can see already prepared locally inclined targets on the titanium basement. The molybdenum powder is pressed in the target area for technetium-99m production. To understand the thermal processes occurring in such targets, a number of simulations were carried out using ANSYS code. As we're going to use a niobium base for target in the future, the main simulations are done with that material. The comparison of niobium, titanium, and copper holders will be brought further. In this slide, temperatures of the irradiated parts of targets and helium flux velocities are shown. The simulation was done for 10 microamperes uniform current distribution over the target area. On the left side of each picture, the temperature scale is shown, and on the right side, the velocity scale. The upper left is for a common flat target. The upper right is for the dual line target, which lines are vertical to the helium flux direction. The bottom left is also the line with the lines parallel to the direction of helium flow. And the bottom right is for the dual axial target. The angle between the ribs is 50 degrees. You can see here the temperature differences for flat and rib targets on the helium side. The differences on the water side are also obvious. The cross-section view of the flat target on the left side and the dual line target on the right with the niobium holder is shown in this picture. The scheme is the same as in the Nirta module. You can see here the water cooling part, which is symmetric to the axial rotation. The DL target looks good. It is also interesting to know the target's basis temperature. So in this picture, the temperature of the targets with their bases are broad. You can see here that all lead targets have close temperatures and are cooler than the flat one. The same is true about the target holders. It will be interesting also to know the temperature of the target holder on the back side where water cooling is applied. Since now we considered niobium holders in the simulations, let's see how the temperatures will change in the case of titanium and copper holders. In this slide, the comparison of three material cases is brought. Please pay attention that the temperature scales are different. This was a necessity because in another case, the temperature distribution visualization wouldn't be enough detailed. The flat targets are shown on the left side, and the dual axial targets are on the right. For dual axial targets, the maximum temperature of the targets are as follows: 38 degrees of Celsius with copper holder, 49 for niobium, and 88 for titanium. The thermal conductivity of the holder material plays a huge role here. If we will calculate the maximum temperatures versus the irradiation current for all kinds of targets with niobium holder, we will get this graph. Here, the notation of the lines is following. Flat, of course, is for the flat target. dA is dual axial. dL with the equal sign is a dual line in which ribs are parallel to the helium flow direction. dLx is the same with the vertical direction. The important thing for the cooling calculations is the heat flux, heat transfer per unit area. There is a concept of the critical or maximum heat flux for each cooling condition from the heater surface to the cooling liquid. When the temperature of the heater surface exceeds the boiling temperature of the cooling liquid by a few degrees of Celsius, the liquid starts to evaporate with small bubbles. Heat transfer to the liquid increases at the bubble formation regime, since additional energy is expended on the evaporation. When bubbles formation rates increase too much high, they form vapor films which cover a large fraction of the heater surface, acting as insulation due to low thermal conductivity of the vapor relative to that of the liquid. The heat transfer starts to decrease dramatically. In this point, the heat flux is the maximum. In this graph, the heat fluxes to the water are broad for all types of targets versus the irradiation current. You can see that all types of locally inclined targets have approximately the same parameters. We recommend using dual line parallel targets as their mechanical strength is higher than the axial one. The fit linear formulas are broad on the left upper part. We can use the KDL coefficient for the flat and dual line parallel targets heat flux ratio. Remember, this is for the target with a niobium base or holder. This means that the same heat flux can be reached on a 1.4 times greater current for the dual line parallel target than that for the flat target. On this graph, you can see the area enhancement coefficient K for the dual line targets, which is the ratio of the DL and the flat target areas, and also KDL coefficient versus the angle between ribs. The circles are for the titanium holders, which angles can't be less than 65 degrees in case of the same rib size. The green rhombus is for the niobium holder with the angle of 50 degrees, and the red triangle is for the copper holder, also with 50 degrees. An additional titanium point for 65 degree is brought in the square gained by ANSYS fluent calculation to compare the ANSYS steady state and the ANSYS fluent versions. They are close to each other. And finally, the KDL coefficient table for copper, niobium, and titanium holders. Remember that this coefficient shows how greater can the available irradiation current be for the DL target compared with the flat one. This is an important final result for all these calculations, and this influences the final isotope production amount or activity in a directly proportional way. For the copper case, the final activity of produced isotope can be 1.5 times higher than in the case of the flat target. And for the niobium, 1.4 times higher than the flat, and 1.3 times higher in case of titanium. And I want to note again that this geometry has limitation by the Nirta solid compact target module. So, the conclusion, the new geometry of the locally inclined target leads to higher cooling efficiency, which allows irradiating with higher currents to produce much more activities of medical isotopes. The prepared sample is suited for Nirta solid compact target module, but can be also implemented for the other types of solid-state target models, including the inclined targets. All kinds of solid target preparations, electroplating, press powder preparation, foils, etc., can be implemented on this kind of target holder geometry. Another advantage of the lead targets is an easier dissolution process, as the target thickness is less than in case of the flat targets. So we are open to collaborations. Thank you very much for your attention. Good beam.